Hello, everyone. Talking today to only the Rowan University students in the STAT 02260. And today I'm going to be doing part 2 of sampling distributions. This is from chapter 8 of your textbook. And if you remember last time, we were discussing what a sampling distribution is. And in the case of a statistic like a sample mean, a sampling distribution would be a list of all the sample means for all possible samples of a certain size. When I say size, I'm referring to how many people are in a survey or how many things are being measured, that sort of thing, okay? So it's size n, small n. All right, and actually I'm gonna go to the PowerPoint that we were looking at last time. And actually, I should turn on sharing. Don't share the screen, you won't see what I'm doing. So, yeah, have to get used to all of this. All right, there we go. So it's like I'm sharing the screen now. So let's go to the PowerPoint. There we go. So this is what we determined last time when the sample statistic is a sample mean. And we wanted to know the mean and the standard deviation of the sampling distribution. That is the list of all possible samples, sample statistics, size n. In this case, it would be a sample mean. The mean of the sampling distribution of x bar is equal to the mean of the population. That's what we determined last time. And also the standard deviation of the sampling distribution is approximately the population standard deviation divided by the square root of the sample size. And this is approximately correct, this standard deviation, if the population is, if this sample is no more than 10% the size of the population. Okay? And that, in most cases, that's true. So rule number 1 is always true, no matter what. And that rule number 2 is a very good approximation for the actual sampling distribution's standard deviation. Now remember, the name of the standard deviation of the sampling distribution is called the standard error. The standard error, right? So that's the term that statisticians use. All right, so let's actually go to the slideshow for a minute. And I think, let's just generate what we just saw. And I think we went over this example last time here, where we had data that suggested the distribution of platelet volume of patients who do not have metabolic syndrome is approximately normal. There's our mean and standard deviation. Those are population parameters. So the mean of 8.25 is for the population. Standard deviation of 0.75 is for the population. We want to generate 500 random samples of n is equal to 5. Remember, or n is equal to 10 or 20 or 30. We end up with these histograms here. And when it's n is equal to 5, what we're looking at here along the x-axis are all of the sampling, all the samples of size 5 are all here, listed here. Most of them are in the middle here. And as you move to the left or to the right, they start to tail off. One of the things that you notice is that the distribution is approximately normal. N is equal to 10. Notice that, again, the middle is somewhere in here. And notice that the standard deviation of the sampling distribution of the standard error is smaller. Okay? Notice that the width here is more narrow than it is over here. And this is true when n is equal to 20 and n is equal to 30. Notice that the mean is approximately the same. The standard deviation gets smaller and smaller. So as the sample size increases, the standard deviation of the sampling distribution decreases, okay? That's an important concept. It doesn't matter what the sample size is for the mean of the sampling distribution. The mean will remain the same. All right. Okay. So this is something we went over at the end of the last session. So when the population distribution is normal, the sampling distribution is also normal for any sample size. I think the previous example was a population that's considered normal. So the sampling distribution is always normal when the population is normal. However, I think we had an example like this. If the population looks like this, where it's right skewed, positively skewed as they call it here, this is not normal. So the population in this case is not normal. Okay. But as you look at the sampling distribution of sample means, and as n is equal to 5, it's still skewed a little bit to the right. And as you increase the sample size, notice that the sampling distribution becomes more and more looking like normal. And actually, when n is at least 30, you could say the sampling distribution is normal. You can see it right here. This is pretty normal looking. We also, of course, see that as the sample size increases, the standard error it becomes less and less. The width of the histogram here becomes narrow. Okay. All right. And we talked about the central limit theorem, which basically says that if the sample size is sufficiently large, the sampling distribution is well approximated by a normal curve, even if the population distribution is not normal. Okay. And what is it sufficiently large? At least 30. Now, this is true for sample means, the sampling distribution of sample means. We're going to be talking about a little bit later today about the sampling distribution of sample proportions. And they use a different rule there to determine whether the sampling distribution is normal. N is greater than or equal to 30 is applied here when we're dealing with the sampling distribution of sample means. Okay, I think we talked about this one last time also. Notice that for the sampling distribution, we use the mean is equal to the mean of the sampling distribution is equal to the mean of the population, which in this case is 12. The standard deviation is equal to the standard deviation of the population divided by the square root of n. Again, we did this last time. I don't need to repeat the problem. The population standard deviation is 0.16. The sample size is 16. And the standard error, which is the standard deviation of the sampling distribution, is 0.04. Notice it says in the body of the problem, X, which is the content of the cola can, is normally distributed. So if the population is normally distributed, that's what it means by X here, then we automatically assume that the sampling distribution is approximately normal, and it doesn't matter that the sample size is below 30 in this case. The sampling distribution will be normal if the population distribution is normal. 16 is still okay. We can use the normal curve to approximate the sampling distribution. And to answer this question here, the question is, what's the probability that the sample mean soda, that is of the 16 cans of soda, we were measuring the content of each one of those cans. What is the probability that the mean, the sample mean of those 16 cans is between 11.96 ounces and 12.08 ounces? In the middle here, we don't have X, we have X bar. We're trying to anticipate ahead of time what the probability that that particular 16 cans of soda have an average content of between 11.96 ounces and 12.08 ounces. And we would use normal CDF to answer this question. Now, in the slides here, what do they use? They use, they want you to convert to a Z. Now, notice here that the Z that they convert to, they use X bar minus UX bar divided by sigma X bar. That's our Z score, standard score. That is, they convert the denominator into sigma divided by the square root of n, and then they convert mu X bar into mu, all right? Because the mean of the sampling distribution is equal to the mean of the population, and they're converting this into the population mean divided by the square root of n, right? So this is the Z that you can use. But since our TI-8384 calculator does all this work about converting X bars to Z's and all of that, we don't need to use this formula. We need to know this formula in general, but we don't need to use this formula to do this probability question. So let's just go back a minute. Here are two numbers, 11.96 and 12.08. The mean is 12, and this is our standard error here, right? 0.16 divided by 4, that's the square root of 16, is 0.04. Okay. So to do this problem, we go into normal CDF. So what I'm going to do is just get out of the slideshow here. 11.96, and what was the other number? 12.08. 11.96, 12.08. We'll go into our calculator. We go into CDF. All right, 11.96 is the lower bound. 12.08 is the upper bound. The mean is going to be 12. And what was that? Go back to the PowerPoint. What is the standard deviation? 0.04. It was 0.04. Just look at it for a second. 0.04. Right. That's our standard error. That's what we're going to use to solve this probability problem. Because this probability problem is asking what is the probability that X bar, the sample mean, is between these values. So we cannot use the standard deviation of population. We have to use the standard error of the sampling distribution, the standard deviation of the sampling distribution, which in this case is 0.04. Scroll down, hit enter, hit enter again, and that's our probability. 0.8186 if we round it. So it's about a little less than 82% chance that the sample of 16 cans, the sample mean of 16 cans will be between 11.96, the capacity of those 16 cans, the mean of the capacities will be between 11.96 ounces and 12.08 ounces. So this is the probability that the sample mean will be between these two values. It's 81.86% chance. And if we go back to the PowerPoint, and let's just go to our slideshow again. Just see what they come up with. Notice that they convert the endpoints to Z's. Well, we don't need to do that. And then they subtract. We don't need to do that. But there's our probability. It's exactly what we found using our TI-8384 calculator. Okay. All right. And again, this is another question here. Let's read through this. A hot dog manufacturer asserts that one of its brands of hot dogs has an average fat content of 8 grams per hot dog, or 18 grams per hot dog. Let's just make sure that, yeah. With a standard deviation of 1 gram, consumers of this brand would probably not be disturbed if the mean was less than 18 grams, but would be unhappy if it exceeded 18 grams. So an independent testing organization is asked to analyze a random sample of 36 hot dogs. Suppose the resulting mean is 18.4 grams. That's the actual mean content of the 36 hot dogs. Does this result suggest the manufacturer's claim is incorrect? Okay. I don't know, how in heck do we answer a question like this? Well, mean is 18.4 grams. That's what they found, right? Now, they said here we would be really disturbed if the mean was less than, would be greater than 18 grams, right? Because it's fat. The more fat, the worse, right? We don't want to eat that in our hot dogs. So 36 hot dogs are looked at, and our one sample we ran showed of those 36 hot dogs an average fat content of 18.4 grams. And we want to know if this claim, if this manufacturer's claim is correct. Now, what did the manufacturer say? That their average fat content is 18. Okay, that's what they're saying. All right, so let's see how they do this problem. Sample size is greater than 30. So this fat content, there's no information about it being normal, being normally distributed, but since the sample size is greater than 30, we're going to assume the sampling distribution is approximately normal according to the central limit theorem. All right. There's the mean of the sampling distribution, 18. Why is it 18? Because it's equal to the mean of the population, which is 18. There's our standard error. It's 1, which is the population standard deviation divided by the square root of 36, 36 being the number of hot dogs in the sample. So our sampling error, or standard error, or our standard deviation of the sampling distribution is 0.1667. What's the problem that we're being asked? Is the probability that X bar greater than 18.4? Well, why did they come up with 18.4? Well, we want to see if we got any results greater than 18.4, okay, in the future, okay, in other sample means. So we want to see if their claim is correct. We're basically asking, what's the probability of getting at least 18.4 grams? Okay. Is it low? Is it high? That's what we need to ask. And then if it's a low probability, then we can say the manufacturer's claim is okay. If it's a high probability that it's 18.4 or greater, if we assume 18 grams of fat, okay. If this probability is greater, well, actually, let's let me revise what I just said, because I think it needs some revision. If we assume that, if the manufacturer assumes that there's 18 grams of fat in the hot dogs, and you get into your sample 18.4 grams, okay, and we're assuming that 18 is the population parameter. If X bar is large, if there's a strong probability that X bar is greater than 18.4, assuming that the population is 18, the population mean is 18, okay, then the manufacturer is good. We can say, yeah, the manufacturer's claim is pretty good. But if this probability is really low, if there's a really small chance that if we assume 18 is the probability of the population, and we're getting 18.4 greater, and that probability is really small, then it's probably not true that the mean of the population is 18. I think that's the reasoning behind it. We'll talk more about that reasoning next week and the week after that. So don't worry about it right now. But this is just an example of some statistical reasoning. Here they're converting the X bar to a Z, and then they're doing the probability. Here we would of course use our normal CDF, and in this case here we would have as our lower bound 18.4. Our upper bound we would use positive 1,000, and then the mean is 18. The standard error we would use 0.1667. And the probability we would end up getting is 0.0082. That's a really small probability. So in this case here, what we're suggesting is that the probability of getting in a random sample of 18.4 or even bigger than that, okay, is less than a 1% chance of getting that type of sample if we assume the mean of the population is 18. Therefore, probably the manufacturer's claim is not correct. Probably the mean is greater than 18. That's really what they're suggesting here. All right. So as I said here, the sample mean of 18.4 is large enough to cause us to doubt that the manufacturing claim is correct. All right. Again, this type of reasoning, I'm not going to test you on this now, obviously, but it will be tested on later when we do hypothesis testing. This is sort of the type of reasoning we'll be using later. All right. Now, the other type of sample statistic that we'll be looking at is what's called a proportion, sample proportion. Okay. Now, what is a sample proportion? Now, when we talked it earlier, and when we talked about what did we talk about earlier? The binomial, right? And we had successes and failures, if you remember, with the binomial. And there was a fixed probability of success and a fixed probability of failure, that sort of thing. And what was, if you remember, with binom PDF and binom CDF, if you remember, the random variable X counted the number of successes. Well, what is a proportion? A proportion is the number of successes divided by the number of trials. In other words, we're converting the count to a proportion or a decimal version of a percentage. All right. So, for example, if we did a poll and 55% of the people in the poll like candidate A and 45% like candidate B, then the proportion would be 0.55 for candidate A. It would be 0.45 for candidate B. So if out of 1,000 people in the poll, 550 of them voted for one candidate A and 451 candidate B. That would be the counts. But to convert them into a proportion, we simply divide 550 and 450 by 1,000. All right, it's simple. It's what we've been, it's what you always do when you calculate percentages. You take your count and divide by the total. All right. So that's what a proportion is. Now, a sample proportion is a statistic. We use P with a hat above it, little hat above it like that. And we use, so that's called P hat, that's our sample proportion. And just the plain old letter P is the population proportion. So we use that. Okay. So you toss a penny 20 times, record the number of heads, calculate the proportion of heads, and mark it on the dot plot. Okay. I guess that's what we're doing. All right. Now, here is the symbols that we're going to use. P is the population proportion. P hat is the sample proportion. Okay. All right. The distribution that would be formed by considering the value of a sample statistic for every possible different sample of a given size from a population. Well, we define that as a sampling distribution. But in this case, instead of looking at the sample distribution of sample means, we're looking at the sampling distribution of sample proportions. We can list all possible samples of size n, and in this case, we're counting the number of votes or whatever we're counting, and then dividing it by the number of people in the survey. We're going to get our sample proportion. We can list all the different samples of size n that we can have, list all of their p hats. We would have our sampling distribution of p hats. Okay. So it's the same idea, except now the statistic is p hat instead of x bar. P hat, of course, is defined as the number of successes in the sample divided by the number of trials or the number of people in the survey, which is n small n. All right, and that it's always p hat, by the way, is always is expressed as a decimal, and p is always expressed as a decimal, not as a percentage. All right, and then we just skip some of this stuff here. I don't want to mix you up. They're just showing you how the following rule is true. The mean of a sampling distribution of p hat is equal to the population proportion. All right. Now remember, before, when we were dealing with means, sample means, mu x bar was equal to mu ux or mu. which is the population mean. So the sampling distribution of sample means was equal to the mean of the population. But in this case, for proportions, the mean of p-hats, that is the mean of the sampling distribution of p-hats, is equal to the population proportion. And here's this fancy formula here. The standard error of p-hats, the standard deviation of the sampling distribution of p-hats. Kind of fancy, right? The square root of p. Now, what is p here? P is the population proportion, right? So it's p, it's a square root. All this stuff is inside the square root. P, the population proportion, times 1 minus p, divided by n, all inside the square root. That is the standard error for a sampling distribution of p-hats. Once again, the sample size has to be no more than 10% of the population size for us to use this rule number 2. Rule number 1 is always true. Okay. Previous slides showed that. You can look at those on your own if you like. But rule number 2 is approximately true when the sample size is no more than 10% of the population size. All right. And again, they're showing you examples as you increase the now these are distributions of p-hats, sampling distribution of p-hats for different sample sizes. Notice that the sample size increases, the distribution of p-hats becomes more and more narrow, becomes more and more like a normal distribution. All right. So again, I'm going to move through these quickly. You can again look at them on your own. I have posted these for you. All right. Now, let's look at an example of how this works. And once we go through this example, once we're done with the example, I will show you some homework problems that I picked out of the book. We'll look over those. I will post these probably tonight, and you'll have access to them. All right. So, development of viral hepatitis after a blood transfusion can cause serious complications for a patient. An article reported that hepatitis occurs in 7% of patients who receive blood transfusions during heart surgery. Okay. So in this case here, P, the population proportion is 0.07. So we always convert the percentage to a decimal. All right. And in this case, they're generating, of course, these p-hats. Now notice that this is always true, by the way. When you're dealing with proportions, if the sample size is not large enough relative to the proportion, and I'll explain what I mean by that in a moment, we're going to get skewness in the sampling distribution, like when n is equal to 10. So as n increases, in this particular case, you notice that the distribution looks more and more normal. Okay. Once again, of course, as the n is increasing, we also notice that the sampling error becomes more and more narrow. Now, here's a rule for proportions. This is just for proportions. When n is large and p is not too near 0 or 1, the sampling distribution of p-hat is approximately normal. You might say, well, how do I really use this rule? It seems kind of vague. So there is a rule that we're going to show you in a minute. All right. But in general, what they're saying is the further the value of the population proportion is from 0.5, the larger n must be for the sampling distribution of p-hat to be approximately normal. Now, this is the rule that you will be using in class, in this class, and it's the rule that you will go with. It's this rule of thumb. Now, this is like the central limit theorem for proportions, okay? Remember, the central limit theorem for sample means said that when the sample size was at least 30, and it didn't matter what the population distribution looked like, you would say the sampling distribution is approximately normal. But we don't use that n is greater than or equal to 30 in the case of proportions. But we're going to use this conservative rule of thumb here. We take our sample size, multiply it by the proportion, p. We also take n and multiply by 1 minus p. And if both of those products are greater than or equal to 10, then we can say that the sampling distribution of p hats is approximately normal. Okay, so that's the rule that we use. Okay. All right. Let's look at this example, and then I'm going to show you the homework, because I want to show you how to apply everything that I talked about today. So once again, this is the proportion of patients who contract hepatitis. This is the population estimate, 0.07. So now we're going to do an actual survey. Suppose a new blood screening procedure is believed to reduce the incident rate of hepatitis. Blood screen using the procedure is given to 200 blood recipients. So that's our sample size. N is equal to 200. Only 6 of the 200 patients contracted hepatitis. Only 6 of the 200. Well, 6 divided by 200, okay, if we do the math, anybody know the answer to that? Is that 0.03, maybe? I think so. So when you take 6 and divide it by 200, 6 is a number of count. It's our count, or number of successes is 6. I don't think you want to call it successes in this case. It's getting hepatitis, but whatever. Out of 200 patients, all right? So 6 out of 200 is 0.03. So that is p hat. You'll see that in a minute. We're giving you the sample results, the sample proportion there. Does this result indicate that the true proportion of patients who contract hepatitis is less than 7%? Okay. That's kind of a difficult question to wrap your head around, but let's see exactly how we answer it. So p is 0.07, p hat from the sample is 0.03. We want to determine, number one, if we can use the sampling distribution, if the sampling distribution is normal. That's what we determined. So we multiply n times p. We don't multiply it by p hat, by p. So n times p is 200 times 0.07. 200 is the sample size times the proportion, the population proportion of 0.07. That's equal to 14. That's greater than or equal to 10. So we're good with that. N times 1 minus p is 200 times 0.93. That's 186. That's definitely greater than 10. So yes, we can use a normal approximation for the sampling distribution of p hats. What is the mean and the standard deviation? The mean is 0.07. Standard deviation of p hat is 0.018, using that square root formula that we saw before. Okay. Does this result indicate that the true proportion of patients who contract hepatitis when the new screening is used is less than 7%? Okay, is less than 7%. So, assume the screening procedure is not effective and p is equal to 0.07. Okay. So what we want to determine is, this is really important to understand in this problem, is if p hat is less than 0.03 or less than or equal to 0.03. We want to see if a sample result, in this case, of 0.03 or less than 0.03, is likely or unlikely given that we're assuming a 7% hepatitis rate. Right, that's the population result that we're assuming. So they're converting the result to a z. We're not going to do that with our we would use normal CDF here. And what we would use in this case here is -1,000 for the lower limit, 0.03 for the upper limit, 0.07 for the mean, 0.018 for the standard deviation, all inside normal CDF. And we would get a probability of 0.0132. So if you did this with your calculator, once again, normal CDF, lower limit, negative 1,000, because it's a less than, right? It's a less than problem here. So negative 1,000, your upper limit is 0.03. Your mean is 0.07. Your standard deviation or standard error is 0.018. That's what you put in for the standard deviation. And then you hit enter, and you should get 0.0132. You won't need to convert it to Z like we did. Now, what did they find? They found that it's a little bit more than 1% chance of getting a sample result of 3% hepatitis rate when we're assuming a 7% population rate. Well, that's highly unlikely, assuming a population rate of 7%. So most likely, the rate is probably less than, the true rate is probably less than 7%. That's what they're saying here. Unlikely that the sample proportion of 0.03 or smaller would be observed if the screening procedure was ineffective. Yeah. So it sounds like it's an effective procedure. But again, don't worry about the interpretation here so much, because this is something we'll be doing later. Just the calculations would be a good thing to do. All right. And that's it for the slides. Now, I'm going to go out of the slides now, and I'm going to pull up some examples here. And we're going to spend about 10 minutes on this. And if you have any questions about anything in this handout, we can address it another time. Now, we're going to go to page 450. And we're going to go to the ebook. There it is. We'll go to problem number 10. Problem 10 says, suppose we have a population with a mean of 100 and a standard deviation of 10. Determine the mean and standard deviation of the sampling distribution for X bar for each of the following sample sizes. So let's go back to the result for that. So now the book uses mu and sigma for the mean and standard deviation. I'm actually using X, UX and sigma X. Why? Because your calculator tends to use those symbols. And also, I want to differentiate between X and X bar, X meaning the population and X bar meaning a sample of a certain size. Now, when n is equal to 9, the mean is still 100. Why is the mean 100? Because mu X bar is always equal to mu X. So it doesn't matter what the sample size is. The mean of the sampling distribution is equal to the mean of the population. In this case, it's 100. Now, the standard deviation of X bar is equal to, sigma X bar is equal to sigma X divided by the square root of n. In this case, n is 9. So it's 10 divided by the square root of 9. 3.33 is the standard error, or the standard deviation of the sampling distribution. Now, in this case here, we're dealing with, we're going back to means, the sampling distribution of means. I know we were just talking about proportions, but we'll get to an example of that in just a couple minutes. And again, what I'm doing here is I'm saying what happens when n is equal to 15. Well, I'm replacing n. Now, the mean is still 100 for the sampling distribution. The standard deviation of the sampling distribution is 2.582. If you get that from dividing 10, which is the population standard deviation, and divided by the square root of 15. All right. So, and then as n is equal to 36, you see that the mean is the same. The standard error goes down even more, and as 50 goes down more, and n is equal to 100, it goes down even more, and 400, it goes down even more. All right. Now, 8.15, I think, shows the same sort of thing. This is on page 451, so let's go back to the book. And go to the next page, 451. We go to number 15. There it is. Where the X, the random variable X this time, is the time in minutes it takes a 5th grade student to read a certain passage. The mean is 2 minutes. Standard deviation 0.8 minutes. This is for the population. If X bar is the sample mean time for a random sample of 9 students. All right, where is X bar centered? Well, that's the mean we're looking at here. And how much does it spread out? That's the standard deviation. And B, we're supposed to repeat the same process with n is equal to 20 and n is equal to 100. And C says, which of those sample sizes would most likely result in an X bar value close to the population mean? All right, so let's again go back to the handout here that I will give you. Here's our mean and standard deviation of 2 and 0.8. And then once again, the mean is always going to be 2, regardless of the size of the sample. The mean of the sampling distribution always 2. But the standard deviation of the sampling distribution, which we call the standard error, goes down as n increases. So what is the standard deviation? Then n is equal to 9. It's 0.8 divided by square root of 9, 0.267. When we increase the n is equal to 20, notice it goes down to 0.179. And then when n is equal to 100, the standard error is 0.08. Now here's the rule. The smaller the standard deviation, the better that X bar is as an estimate of mu. That is, the better X bar will be as an estimate of mu. That's because the X bars, the greater the sample size, those X bars are going to be, in general, closer to mu than if the sample size is smaller. All right, so the answer is always the bigger the sample size, the X bars will be closer to mu. That's n is equal to 100 is the answer to this question. That's part C. It's the answer to the question, which of the samples would have the best estimate of X bar in terms of mu, and the answer would be n is equal to 100 because that's the smallest standard error. And then finally, on page 451, number 19, I wanted to show you this one. Let's go to back to the text. Number 19, I like these types of examples because it's practical examples. It says a manufacturing process is designed to produce bolts with 0.5-inch diameters. Once each day, a random sample of 36 bolts is selected, and the bolt diameters are recorded. So this is a sample of 36 bolts each day. And this is what happens. If the resulting sample mean for this 36 bolts on any particular day happens to be less than 0.49 inches or greater than 0.51 inches, the whole manufacturing process is shut down and they do some adjustment. Maybe they adjust the machines they're using or whatever. All right. So anyway, 0.5 inches is the assumed population mean. That's what they mention up here, 0.5. And they also assume that the population standard deviation is 0.02. Says, what is the probability that the manufacturing line will be shut down unnecessarily? Now, what do they mean by that, unnecessarily? That means they will shut it down, and yet the population is 0.5. It shouldn't have been shut down. Okay, so you shut it down, but the population mean is 0.5. Well, that's what we're going to assume. We're going to assume the mean is 0.5. That's what we're going to assume. So, if that's not too confusing to you. So let's go to the, this is number 19, let's go to the handout here. And there's our mean, there's our standard deviation, there's n is equal to 36. And notice what we're finding. We're going to find the probability that X bar is less than 0.49 or greater than 0.51. That's the probability that the line is going to get shut down. It's either going to be less than 0.49 or greater than 0.51. On any particular day. If that happens, the line is shut down for adjustments. We're assuming that the true process mean is 0.5. That's what we mean by being shut down unnecessarily, because it's being shut down and yet the population is 0.5. So since n is equal to 36, which is greater than 30, we can use the central limit theorem to assume that the sampling distribution is approximately normal. So how do we find this probability? Well, probability of X bar less than 0.49 and the probability X bar is greater than 0.51, they're mutually exclusive. Remember that term from probability? And when we have the word or here between these two here, it says add, right? And since they're mutually exclusive, we don't have to worry about any common elements between these two. And X bar is less than 0.49. It has nothing to do with X bar is greater than 5.51. They can't occur together. So they're mutually exclusive. All right. So we can simply say that that probability up here is equal to the sum of these two probabilities. And how do we find them? We use normal CDF. This one, we're going to use the lower endpoint of negative 1,000. The upper endpoint 0.49. The mean is 0.5. And notice what I do here. I don't try to estimate the standard error. I just put in the whole formula into normal CDF. Sorry about that. All right, 0.02 divided by the square root of 36. Don't even try to estimate it. Don't try to calculate it. Put the whole formula in there. The 0.02 is the standard deviation of the population, and it's divided by the square root of 36, which is the sample size. Close parentheses. Plus, probability of X bar being greater than 0.51. Well, it's normal CDF. We're going to use our lower endpoint, 0.51. Our upper endpoint, 1,000. Our mean is 0.5. And here's our standard error again. Just put it in as is. You can put it in as a formula. Notice that each probability, when we calculate it, is 0.00135. And we add it together, we get 0.0027. The probability that it will be shut down, given that the true mean is 0.5, is very, very low. There's a very low chance that this process will be shut down. Okay, and that's good because you don't want it shut down every day, right? And what it says basically is 27 days out of 1,000 days. That's what this 0027 is saying. 27 days out of 1,000 days is the process shut down. I think most manufacturers would feel good about that. All right, so let's look at a couple more problems and then we're going to close out for the day. Now, this deals with proportions. This is on page 456 of your text. We're going to go to page 456. And it's number 23. I think that's what? Yeah. And in this particular case, they want you to do what we did earlier in the I think it was 8.10. But now we're doing this with proportions. Here's your proportion of success, 0.65. All right, so that's your population proportion, 0.65. And you're supposed to estimate the mean and the standard deviation of the sampling distribution of p-hats. Well, the mean in each case is going to be 0.65. That's going to be the mean because it's equal to the population proportion. The standard deviation, however, would be different. And it will be determined by using this formula, the square root of p times 1 minus p divided by n. For example, when n is 10, we would multiply 0.65 times 0.35, which is 1 minus p, divided by 10. Take the square root of all of that, you get 0.1508. Do the same for 20. Just replace the n with 20. You get a smaller standard deviation. Replace the n with 30. You get even a smaller standard deviation. Okay. Then on page 457, 830, let's look at that one. That's the last one we're going to look at today. 457, that's our next page, I believe. So we'll go to the next page. All right, and I think we're looking at number 30. This is another type of problem I like also. Suppose that a particular candidate for public office is in fact favored by 48% of all registered voters. Now, obviously you would not know this necessarily, but we're going to assume that we sort of have an estimate of the population proportion. That's 0.48, right? When we convert 48%. So that's P. P is 0.48. What does that mean? This candidate's going to lose probably. If there's only one other candidate, the candidate's probably going to lose. All right. So a polling organization takes a random sample of 500 voters, and we'll use we will use p hat, the sample proportion, to estimate p. All right, so 500 voters, that's n. That's our sample size. What is the approximate probability that p hat will be greater than 0.5? That is, what's the probability that the sample shows that this candidate's going to win when in fact the candidate's going to lose? That is, the true proportion is 0.48. All right, so that's really what we're asking here. So let's go to the actual result here. So P is 0.48, N is 500. Remember, the mean of the sampling distribution of p hats is equal to the population proportion, so that's 0.48, and the standard error is square root of p times 1 minus p divided by n, and it's 0.0223. Now that's, I just estimated it. Again, this is the formula right there with the square root. So what we want to know is the probability that p hat will be greater than 0.5. That is that's the probability of the person winning, given that the true proportion is 0.48. All right. But first of all, we have to use the normal distribution to answer this question, which we always want to do. We want to verify that we can use the normal, approximately a normal distribution for the sampling distribution. So we use NP and n times p and n times 1 minus p once again. We use 0.48 as our population proportion. We multiply by n, which is 500. We get 240. And then n times 1 minus p is 500 times 0.52, which is 260. Both of them are greater than 10. So we can use the approximately, we could say that the sampling distribution of p hat is approximately normal. So that means we can use normal CDF to answer the probability question. So what is the probability that p hat is greater than 0.5? You say normal CDF. The lower endpoint, of course, is going to be 0.5. The upper endpoint, again, we use 1,000. The mean is 0.48. And notice for the standard deviation, I just put the formula in. I don't try to put in the estimated value. Just put the whole formula in. The calculator knows what that is. And when we calculate it, the answer is 0.1854. So that's the answer to it. All right. So anyway, I'm going to stop sharing now. And I think it's time to end our little meeting today. I hope it was helpful. Again, what we're going to be doing in this course is also have a Q&A, which obviously would be used, number one, to answer any questions from these videos, and also from the homework also, or just any general questions. Because of the test this week and the fact that I'm running a little bit late, I think our first Q&A will be next week. All right. I don't think you're quite ready for a Q&A anyway for tomorrow. Tomorrow's Friday already. So we'll just plan on a Q&A next week and just accumulate your questions, and then we'll I'll announce when the Q&A is. All right. So anyway, have a very good day, rest of the week, and I will post the this PDF of these solutions for these sample questions from Chapter 8. I will post that also so that you have that. And also, obviously, I will post this video tonight. Obviously, you won't see it until I posted it. All right, anyway, that's it for today. Thanks, and we'll see you later.